Hello, welcome back to Grizzly Adams Mathematics. I'm your host, Tony Weathers, Professor of Mathematics at Adams State University, located at 7,544 feet above sea level. Today we're going to take a look at one of the most famous mathematical constants of all time, pi. No, not that kind of pi. Yeah, there we go, that pi. Pi, as you may know, is an irrational number, which means that it has a decimal expansion that never terminates nor repeats. What this means is that it is physically impossible to write down a decimal number that is exactly equal to pi. This has led to some attempts to make nice rational approximations to the number pi, and today we're going to take a look at some historical attempts to use geometry to come up with better and better rational approximations to the irrational but extremely important number pi.
We'll begin by defining pi as the ratio of the circumference of a circle to its diameter, like this, where c represents the circumference and d stands for the diameter. One of the first remarkable things about pi is that this relationship holds true for a circle of any size whatsoever. The godfather of geometry, Euclid, never actually addressed the value of pi, but he does have this to say about circles. Circles are to one another as the squares on their diameters. When he mentions circles here, of course, he's referring to their areas. Now, with modern notation, using a script uppercase C to represent the circles, we can write the ratio like this, which, if we substitute the area formulas and cancel the common factor, rewrite in terms of the diameter, we can see that the validity of Euclid's statement relies on the independence of pi from the size of the circle involved in order to be true. Of course, there were mathematicians before Euclid. Some of humanity's earliest attempts to understand the world mathematically took place alongside the fertile river Nile in what is still referred to as Egypt. In a document known as the Rind Papyrus, instructions are written for calculating the area of a circle. With the specifics of the measurements removed, the instructions basically say to cut 1/9 off the circle's diameter and construct a square on the remainder. If we assume a diameter of 1 and compare the modern formula for the area of a circle to the square described by these instructions, we can solve for pi over 4, then for pi itself, to see that the Egyptian scribe was effectively using a value of 256 over 81 for pi, which in decimal looks pretty close to 3.1605, which is a scant 1.89% too large and not too shabby for nearly 5,000 years ago. A passage from the Bible states, "And he made a molten sea, 10 cubits from the one brim to the other. It was round all about, and his height was 5 cubits, and a line of 30 cubits did compass it round about." This particular passage comes from the first book of Kings, but substantially the same description appears in 2 Chronicles as well. If we take the description literally, using 10 cubits as the diameter and 30 cubits as the circumference, we have the value of pi is equal to 3, which is about 4.5% too small. The towering ancient intellect of Archimedes also tackled the question of pi's value. He used a novel approach of circumscribing and inscribing hexagons about what we would call the unit circle. By doubling the number of sides repeatedly, he eventually reached a 96gon, which left him with the upper and lower bounds shown here. Now these bounds, as you would expect from Archimedes, are very, very good. In about the year 480, a Chinese mathematician named Zhu Chongqi gave the remarkable approximation 355 over 113, which in decimal looks like this. In addition to its clever and easy to remember pattern, it is astonishingly close to the real thing. Finally, we come to the end of the era during which mathematicians used geometric approaches to approximate pi, with François Vieta, who, in 1593, used a clever bit of geometry to show that pi could be written as this expression. Using this fact, he calculated that pi was approximately equal to this decimal number, which is just ridiculously close to the real thing.
To get an idea of how these approximations stack up against each other, let's imagine using these various approximations of pi to calculate the circumference of the Earth. We'll assume, for the sake of simplicity, that the Earth is a sphere with a diameter of about 7,926 miles. If we use that figure, along with pi equal to 3, the figure from the Bible, our calculation of the circumference of the Earth would be off by about 1,122 miles. If, on the other hand, we use the figure from the Rind papyrus, 256/81, our answer would only be about 150 miles off, but this time too large. If we use 22/7 from Archimedes, we get a much closer figure, 10 miles off. Using Sue's figure, our circumference of the Earth would be off about 11 feet too large, and remarkably, if we use Viet's value, we would get 0.3 inches too small. This underscores how good Vieta's approximation to pi really is. Well, that's all for this time. Thank you for watching this video, and please remember to check back for more interesting videos later.